Thanks. So, as I'm sure everyone's aware, SNARKonomicon, it's an ancient book of, eldritch magic. It was discovered in the 1500s. Okay, people don't like that joke. I apologize, this is in black and white. Also, my computer broke, so I couldn't do the color, but it would have looked even more terrifying. We're going to discover what is this SNARKonomicon exactly more in the talk, but I assure you it's not as terrifying maybe as the name sounds and as the devil on the picture suggests, but we'll find out. Okay, so just a bit about me and where I'm coming from. So I'm Izaak, that's me on Twitter. I work on Coda, which I'll say a second about, and also Snarky, which is a zkSummit programming language, which we'll talk a lot about such things in generalities. So Coda is a cryptocurrency that uses recursive composition of SNARKs for blockchain accessibility and scalability. So accessibility meaning basically anyone can verify the entire state of the chain, even on a phone by checking a SNARK. So if you saw the first talk, it's sort of a similar concept. You can kind of compress down the entire blockchain by using SNARKs. So I've written probably, I think, someone can correct me if I'm wrong, but probably as much SNARK code as anyone else. And this talk is an attempt to distill some of what I learned. This is of course drawing on the work of many people, but I hope you'll learn something. Let's get started. Who, maybe just to get a sense of the audience, who has programmed a SNARK? Okay, great. So almost everyone will learn something. And who even knows what I would mean by SNARK programming? Okay, maybe more people have some sense. That's good. Maybe this thing is mind-numbing for. No. Let me not say that. Maybe some people have seen almost this exact slide on everyone else's talk before. So if so, I apologize. But just to set things up, let's say just to kind of say what do SNARKs actually do. For a given program, P, with, say, 2 arguments and a public value X, okay? What SNARKs let you do is they let you prove statements of the form, I know some secret Y, so that if you run P, my program, on X and Y, it will output 0. Okay, that's what SNARKs let you do. In such a way that the proof is, well, first of all, it reveals nothing about Y, so it's zk, zero knowledge, right? It's small, so like less than a k. For a Stark, maybe you can ask, but and easy to check. So the verification time is on the order of milliseconds in practice. So then what we said here, program, right? Program P. Well, it's a program. What programming language is it written in, right? A program means a program in some programming language. Maybe it's x86 assembly. Who thinks it's x86 assembly? Anyone? Huh? Ah, yes. Well, perhaps on some level. C, maybe. Python? No, I don't think so. Haskell? No, it's not Haskell either. It's actually something else. And what is that something else? So, just to kind of say, like, SNARK programming, it's programming. It's programming this function P that we saw a few slides ago. But with a different machine model than all of the languages on the previous slide. Okay, so usually you think about, at the end of the day, it's going to be running on a RAM machine, right? A machine with a CPU that goes to memory, that does its fetches and computes, right, step by step like that. But in SNARK programming, you have a different machine model. Just a note about terminology. People often talk about programs, or really what they mean is like a computer program, meaning a program which is intended to be executed on a CPU. SNARK programming just means a program which is intended to be executed, for whatever that means, on SNARKs, okay? And of course, anything can be executed on anything else, but it's somehow about the attention. Let me say, most of this is not really specific to SNARKs. Some of it is sort of, but most of it also would apply to something like a bulletproof or like SNARKs, okay? So it's just about the ideas here of how you think about the conceptual models of programming, mostly, and some of the tricks. Okay, so what about SNARK programming is different from quote-unquote normal programming, or as I call it, CPU programming. No, I don't call it that, but programming. Well, one is the cost model. So what is it that's efficient? Two is, in SNARKs, you have this magic superpower, which is called non-determinism. Don't worry if this is a scary sounding word, or if you don't know what it means, I'll talk about it. And the third is that you can only inside of a SNARK somehow access a small amount of data at a time. In a way, it's not so different from a CPU. You know, a CPU is this like tiny thing, and over here is like the giant memory, you know, and the CPU just sees a small amount of the memory at any given time, right? But in a way, it's not so different. So let's first talk about the cost model. And in terms of what primitives, what are the sort of efficient primitives that you have access to in both settings? So on a normal computer, who has programmed a computer? Oh, that's great. I mean, it's not every room that you're in that, almost everyone raises their hand, so that's great. So in a normal computer, what do you have? You have like, say, plus and times mod, 2 to the 64, say, 64-bit ints. You have memory access, you can load and store from memory. You can do bit stuff, so, and or and all that. And you have conditionals, jumps, basically. SNARKs, what's the deal? So, well, first of all, you have plus and times mod some large prime p. It's not so different, somehow. The p is a bit larger, but anyway. This is really important. Plus is like kind of free-ish. Okay, so plus costs 0-ish. When you're programming, this is how you think about it. Plus is almost free. Times costs 1. Does that make sense? Addition is like free. Times is not free. Cool? Make sense? Okay. And, okay, what else you have? Well, no, actually, that's pretty much it. So, you might be a little bit worried and say, oh no, really, that's it. You might say, well, this seems really bad. And this is the SNARKonomicon demon who is laughing at you. You only have plus and times. And sometimes when I think about this situation, I go back to this famous painting of Hieronymus Bosch from 1575 called SNARK Programming, ? Which illustrates some of the interesting aspects of SNARK programming. You see here you have the large prime, and here is the multiplication. And you might look at this picture and think it looks a little bit scary. There's people burning and so on. But actually, it's not so scary. One, this place looks pretty cool. There's a giant person with a giant mouth. And two, you're allowed to do some other stuff too. I kind of lied. It's not just plus and times. For example, you have non-deterministic choice. Which we'll get into, and you can sort of compute on values as normal as long as it's only sort of statically known things, which is actually useful. Okay, so yeah. So the goal of this talk is basically the following. It's to convince you and show you how to make this a comfortable and exciting place to live. Some of these things which look scary, like the guy with the big mouth, maybe actually he's a nice guy, for example. And the major takeaways will be the following. One, SNARK programming is both beautiful and fun, just like programming. Non-determinism is a really powerful technique, but it's kind of scary, and we'll talk about what's scary about it. And three, there are a lot of really great, cool ways that you can sort of do things efficiently just by using field arithmetic that you have in this huge field, that aren't things that you could necessarily do on a normal computer. And I'll try to give some examples in Snarky, which is this SNARK programming language of the concepts that we discuss. And you could also think that, at the end, you will see this SNARK demon and not think that he's tormenting you, but actually you will think that you're laughing with him about how great and fun SNARK programming is. Just a word about notation. We'll fix this large prime p that you have addition and multiplication for. You should think this large, but in the talk I'll use 13 in examples, which for a human is large. But you should think of it as like 2 to the 256, realistically speaking. And a number in 0 to p, you call that a field element. Okay, people know this? Okay. Okay, so just like, let's look at a SNARK program. This is a really simple program. What does this program do? Well, okay, who heard about elliptic curves before? Oh, okay, a lot of people. Well, even if you didn't, it doesn't matter because they're extremely simple. They're just a set of solutions like x and y to an equation that has this form. Okay, cool. And you know, geometrically speaking, say over like real numbers is what they look like. All right. So this is just a really simple program that just does this arithmetic, right? We said we could do plus and times. Let's do plus and times, just to introduce the notation. So you know, I say a is 1, b is 4, whatever, and here's the function that just computes you know, the right hand side here, right? X times x times x plus a times x plus b. Okay, does it make sense? And this is saying this is a function, right? This is kind of like looks like JavaScript maybe, ish, yeah. Everyone with me, sort of? Okay. So it's a function. That's just to give you an idea of what the syntax looks like. Now let's talk about non-determinism, which is quite interesting. So who heard about non-determinism? I know I keep asking people. Oh, that's cool. So sometimes, as people might know, checking is easier than doing something yourself. Who has had this experience in their life? That they were able to check something that someone did and it was easier than had they done the work themselves? Probably everyone has had this experience. Unless you sit in your room all day and don't interact with other people, I would imagine that you checked what someone else did at some point in your life without doing it yourself. So everyone knows somehow this is intuitively true. And what's cool is that this non-determinism power that you have in SNARK programming, it lets you go from being able to just check something to being able to do it, which sounds pretty nice. I imagine we would all like to have this, this power. I guess that's called delegating responsibility to other people. Anyway. So let's have an example, a concrete example of what using this non-determinism power looks like to do a very simple computation. In some sense, it's the simplest possible computation. And that computation is dividing numbers. So if I give you x and y, and you can do multiplication and addition and nothing else, let's say, how are you going to compute x divided by y? Okay. Another way of saying this, you want to find some z so that z times y equals x. People see that you divide by y and it says z is x divided by y, right? Okay. So you just want to find a z where that's true about z. So one, I know it's a simple, silly example, but it's a really and very important function. You need it to efficiently implement elliptic curve arithmetic, which you need for doing anything inside of SNARKs. Hash function, Peterson hash, signatures, VRF, recursive composition, the list, it just goes on and on. So let's give a deterministic algorithm. It's probably not the best one, but it's the easiest one to think of for computing x divided by y. So what's the algorithm? Who knows Fermat's little theorem? Maybe fewer hands. Okay. So this says that if you raise a number to the p minus 1 power, then it equals 1, mod p. Okay, of course. So it means that you can do division by doing multiplication in a finite field. You just multiply. You don't really have to worry about it. The upshot is basically you compute x divided by y by multiplying x by y to the p minus 2. Okay? So you can do division by doing multiplication. It's kind of cool, actually. But actually, it's not that cool because this is expensive. You have to do like 256 multiplications, roughly, to compute this exponentiation. And that's just for one division. So you might already be kind of like, SNARKs, not so good, huh? Yeah, this is definitely bad. But what about checking a division? So like, let's say if someone gave you z, right? How many multiplications would you need to check that z is x divided by y? Who knows? Huh? One, right? Just one. You just check that z times y equals x, right? That's it. It pins down z exactly. So that's great because in SNARKs you have this guess and check power, which is another way of saying you can do non-deterministic choice. You have a magic guess function. It's magic. In Snarky, it's called exists because you're like, this exists. It's like guess. You also have a magic check function, which lets you make assertions, which you can, like an assertion in normal programming. It halts execution if the assertion fails. It's like throwing an exception. And I call assert. So, diagrammatically, here's how you do a division if you can magically guess things. So you guess a z, right? And then you just check that z times y equals x, and then you return z. Does that make sense? Conceptually, I say, I want to compute x divided by y. First, I guess z by magic. And then I just check, does z times y equals x? If so, the assertion passes, I go to the next line, I return z. Otherwise, execution halts, and okay, that's it. So, just to do an example, let's say we want to divide 6 by 2. I guess, conceptually, you first think you're sort of making all possible choices, z equals 3, z equals 4, whatever, and then you check each one. So, okay, 3 times 2 equals 6, yay. 4 times 2 is 8, not 6. So there, execution halts. 5 times 2 is 10, not 6. So there, execution halts again. And so, this is sort of the only branch that we take in reality. So, okay, just like let's crank through it. So, okay, we did 6 over 2, right, that was 3. 1 over 2, I guess it's 7. I'm going to guess that. And in fact, I'm right, because we're working mod 13, if anyone remembers from that slide way long ago. Because 7 times 2 is 14, which is 1 mod 13. How about 0 divided by 0? I don't know, maybe 0. That seems like a good guess. Let's check. 0 times 0? What is it? It's 0. Okay, great. So I guess if I divided 0 by 0, it's 0. Oh, what about dividing 0 by 0? Well, I don't know, maybe it's 5. Let me check. Oh yeah, 5 times 0, it's 0. So I guess dividing 0 by 0 is 5. So dividing 0 by 0 is 0. Dividing 0 by 0 is 5. Which maybe you think the SNARK demon is coming to haunt you again. And yeah, that is a little bit troubling. So everyone take this in, okay? This is like understand non-determinism. It's either, right? I mean, you sort of don't know what div 0, 0 in some sense is going to return. It could return anything which would make all the assertions pass. In particular, well, it could return 0 or it could return 5. You don't know. And you have to think about it that way when you're programming. So there's a few things you can do about this. You can add an assertion, basically, that says y is not 0, like the second argument, say. That would cost you an extra multiplication, so, not great, but still a lot better than 256, right? So now it costs 2 instead of 256. So that's pretty good. Another thing is you could change the name of the function from div to div unsafe and forget about it. And that's an emoticon. It's a sideways. Okay. So, just like to show you what this looks like in code, yeah, as I said, you have a magic exists function, and this is just how you write it. So you say, okay, guess z, so let z be, I don't know, guess, and then assert that z times y equals x, and then return z. Okay? So it's kind of what I said. Cool? Okay. How am I doing on time? Does anyone know? 10 more minutes. Okay, that's probably enough. Okay, so let's just, you maybe think, okay, very cool, you can divide numbers, great. When am I going to ever have to use this in real life? Non-determinism. Well, you will have to use it in real life. It comes up all the time. And to just revisit our previous example, you remember we had this, this was literally, this was the slide before. We had this elliptic curve, and we had this function f for computing the right-hand side. Here, x cubed plus ax plus b. So what if, we wanted to start with an x-coordinate, like, here's something that you have to do in SNARK sometimes. Sometimes you have to decompress a curve point. Who knows what I even mean by it? It means you start with the x-coordinate, and if you look on this picture of an elliptic curve, corresponding to every x-coordinate, there's exactly 2 points on the elliptic curve corresponding to that x-coordinate, because you can solve for y. You just take the square root of f of x, right? But it could be plus or minus, so there's 2. But the thing is, right, there's only 2, so that's pretty cool. So sometimes you just have the x-coordinate because it's more efficient, maybe. You don't have to have both the x and y to determine the curve point. You just need the x-coordinate 1 bit. So one thing that you would want to do is decompress a curve point. So given just the x-coordinate, you want to compute both the x and the y. And in SNARKs, it's super easy. What do? You say guess y, okay? And then just assert that y squared is equal to f of x. Done. And then you just return x and y. Does it make sense? You guess and then you check. You guess, oh, maybe it's y. Let me check. Okay, I checked. Yep, it was y. I returned y. And so what you return here is only the y's which make this equation true. But it's a little bit scary because, right, so it could be this y, but it could also be this way. So you don't know, is this going to return that one or that one? You would have to add more checks to pin down one or the other. But okay, whatever. Sometimes maybe you wouldn't care. So just like to wrap up, takeaways about non-determinism. Yeah, when you're trying to write non-deterministic programs, you think more about specs than algorithms. So, this is like a spec, right? I'm saying basically return y where, y squared is equal to f of x. You see what I'm saying? It's not really an algorithm. It's just a spec. It doesn't tell you how to find y. Another thing which, I probably was clear, but non-determinism gives you essential efficiency improvements. So you can't write efficient SNARK programs without using non-determinism. I mean, I don't know, maybe someone will tell me I'm wrong, but no, you can't. But it's also really scary, right? So we saw this like div 0, 0 thing, remember? Where like if you divide 0 by 0, it could be anything. So that's really actually extremely scary because you can't rely on anything actually about the output of that function. It's totally unconstrained, which means maybe you're just using division inside of an elliptic curve operation, but at the end of the day, what it means is you sort of allow the attacker. I mean, you think in your mind always about a malicious prover. I guess I should have mentioned that. You always imagine there's a malicious prover who's trying to sneak bad values past all of your assertions. You see what I'm saying? So that division function is really scary because it lets them sneak whatever value they want through your assertions, which is potentially really bad. So you try to build abstractions that somehow use the non-determinism internally but don't leak it if possible. So for example, with division, if you assert that y is not equal to 1, or not equal to 0, then you don't have to think about it anymore. You know it's sort of really a function. It doesn't have non-determinism. Let me say something about taking advantage of arithmetic. All right, 5 minutes. There's non-tricky techniques, and those are like using elliptic curve-based primitives that I think people kind of know about this by now, but there's like the Peterson hash function, for example, which is like 20 to 30 times more efficient than like a bits style hash function, like SHA or Blake 2. And another non-tricky thing is just simulating integer arithmetic. So field arithmetic is sort of, as long as you don't overflow, it's the same as doing integer arithmetic. But then there's also tricky techniques. So these are the things that make the SNARK devil smile, and that also make us smile. So for example, there's packing. Okay, I'm not going to talk about it, but then there's also this technique that I didn't really have a word for it, but I called it sum as search. The idea is addition is free, and we want to make use of that. So I'll give you the simplest possible example of this. Just something to take home with you, and later you can go online and read more SNARK programs and assimilate this idea, and you'll see it in multiple places. So bools inside of SNARK programs, we only really have field elements. So how do you represent a Boolean? Just with a field element which is only 0 or 1. Okay, it's a field. We have 0, we have 1. Okay, happy? Are we happy? It's maybe not the best representation for all purposes, but it's pretty good. So with this representation, everything's pretty easy to talk about. All the bit stuff you know and love from normal computers. The greatest hits, we got them all. It's 1 minus x, right? So because if x is 0, then 1 minus 0 is 1. If x is 1, 1 minus 1 is 0. So it's not, right? We got and. It's just multiplication, right? Because 0 times anything is 0. Like false and anything is false. And true is 1. It's true. So it's 1 times 1. Make sense? Yeah. Okay. And then if you have not and, you can do or, for example, with just De Morgan, I guess it's called. So x or y is true if they're not both false, right? And then you can kind of say like any, right? So if I have an array of bits, I want to return a bit which is true if any of them is true. You see what I mean? It would be doing like b's of 0, the zero thing, or the first thing, or the second thing, or the n-1 thing. Okay? And you just write, reduce, like functional programming. Does it make sense? Do people see what I'm saying? Okay. So this is okay. What's the total cost of this? Remember, we only care about multiplication. This costs n-1 multiplications because each of these ors here costs 1 multiplication because it's coming from this. So that's okay, I guess, but actually you can do even better. How much better? You can only use 2 multiplications regardless of how many things you're oring together. And what do? Well, you just take all your bits and you add them up. Okay? You just add them. Like, they're numbers, they're field elements, you can add them. And then you just check, you look at that sum, and you say, hey, is that sum equal to 0? Right? And if it's not equal to 0, it means one of them had to be non-zero. Right? Does it make sense? Do people see? Maybe it requires a moment of thinking. Okay. No? No? Okay. So this is great because this only costs 2 multiplies rather than n-1. They're inside of equal, but I won't show them. So this is, maybe after. So this is, a neat trick. You're kind of searching the whole thing by adding everything up. But addition was free, so it doesn't matter if you add up everything. It's free, ish. So I'm almost out of time. Let's see. Yeah, so some important things that I wanted to talk about but couldn't talk about. One is it's one thing to write exists, to just write guess, but you actually have to find that value because it's on a magic computer. As someone back there said, it is executing on a normal quote unquote computer. So you need to actually specify how to find that value. This maybe someone would call witness generation. And the other thing I didn't talk about is how to simulate large memory banks. Remember when I was like, oh, you're a small CPU and the giant memory is over here and you need to reason about it. So I didn't talk about how to simulate that. That's an interesting technique. There's a lot of cool efficiency hacks you can do there too. But I also didn't talk about mixing SNARK code with normal code. It's another important thing. And that's pretty much all I have, so thank you.
We have time for a couple of questions.
Yes, hi. Thank you for this very interesting presentation. Is there an intuitive explanation of why addition is so cheap and multiplication costs 1?
Let's see. Right now I'm simulating like the whole reduction in my mind to think about where it happens. I don't know. It's a very particular artifact of the construction, I think. But addition is always a lot easier. Maybe it shouldn't be so foreign because addition is always a lot easier than multiplication. It's kind of a cop-out. But we'll talk about it after, and I'll trace through the reduction and remember where it happens. I don't remember off the top of my head.
Other questions?
The reduce example, when you use sum instead of multiplication, it could still overflow, right?
Could it? So P is, let's say, the prime is like 2 to the 256. So you're adding up like, how many bits would there have to be for it to overflow? Like 2 to the 256, which is not a real number. I mean, it's according to some people, it's an actual number, but it doesn't exist. You would never construct that many bits in the universe. Let me say it that way.
Right.
Yeah. So you do kind of hacks like this where something is sort of okay, but only for cryptographic reasons, I guess.
I'm curious, like in your current circuits, what percentage is Booleanity checks, and if you have a smart way to aggregate those?
What percentage? I mean, it's definitely a lot, because most of it's the Merkle. Probably everyone knows the worst thing is doing a Merkle lookup. The worst thing is doing a memory load in a SNARK. That's like, I guess it's the case with real CPUs too. That's the worst thing. But I don't know percent. But yeah, that would be. I don't have a smart way. That would be great.
How do you test to make sure that there's no problem in non-determinism?
Yeah, that's a great question. No. That's really a great question because, as I said, it's really scary. The SNARK demon sometimes haunts me in my sleep, thinking like, oh no, did I put enough constraints? But yeah, I mean, so we do unit tests. You can kind of just try and stuff values in there and see if you can make the constraints pass. Obviously, that's not really going to cut it for most cryptographic applications because there the errors are like on points that you would never find if you're testing randomly. But we've started a little bit looking at doing some formal verification, so like doing some calc proofs, but that's in early stages, and right now it's you get a lot of people to read the code and think about it very hard. The other thing is I always write pen and paper proofs, or in the comments I put proofs, but that can even only get you so far.
I think we have to wrap up the questions and move those to the coffee break afterwards and start preparing our next speaker. So thank Izaak very much again.